Hello, multivariable calculus students. This is Mr. Johnson, and we're going to finish up section 11.4. We're going to look at tangent planes to parametric surfaces. So we're going to make a connection now to our past couple chapters, and we're going to look at vectors. So remember, back in chapter 10, we talked about a parametric surface in vector form, so a vector of two variables that would produce a surface. And the partial derivatives would be as follows. It looks really complex, basically. All it is going to be the partial derivative with respect to u, for example, over here would just be each component, that derivative with respect to u, and the same for v. We talked about that in chapter 10. So let's talk just about what this actually means in terms of a plane. So if you had a particular surface in space that was represented by r of uv, and you had the partial derivative with respect to u and the partial derivative with respect to v, you would have two little tangent vectors at a particular point on the surface. Those two tangent vectors are going to lie in the tangent plane. So in other words, if you were to picture the tangent plane on this particular surface at this particular point, these two vectors are in the tangent plane based on curve 1 and curve 2, which is represented by these partial derivatives. So in other words, the partial derivatives themselves treat one variable as a constant. So the partial derivative with respect to u treats v as a constant, and therefore it would be just a curve along the particular surface. And the derivative then at that point would simply be just the tangent vector to that point. And that tangent vector, along with the other tangent vector in the direction of v, would be in the tangent plane. So that's a lot of review from chapter 10 that we already discussed. The idea here is that if we want a tangent plane and the surface is not given in Cartesian form, but rather in vector form, we want to be able to come up with the equation of that particular tangent plane using our vectors. Okay, and here's how we do it. And it really just dates back to our last couple chapters. So if the cross product between the partial derivatives r of u and r of v is not zero, the surface is considered smooth. So in other words, we have, thinking back to single variable calculus, we do not have any cusps or sharp corners. And so we have a smooth surface. The tangent plane is the plane that contains the vectors r sub u and r sub v. So that's what I just stated, and I kind of gave a quick visual based on your notes as well as the background for it. The vector ru crossed with rv, so the cross product of these two vectors, remember from chapter 9, would produce a vector perpendicular to both in one of these two directions, which would by definition be perpendicular to the tangent plane. And it is therefore the normal vector to the tangent plane. So this is a huge concept that is connecting chapter 9 with chapter 10 and now to chapter 11. So remember, I mentioned this in the very first video of this section, but here is the equation that we've used in the past for the tangent plane, and we are going to now use this again. This time, however, we're going to use the partial derivatives of the vectors to come up with the normal vector. If we have this surface written in such a way that we have r of uv. So the normal vector, which is made up of a, b, and c, is simply the cross product between these two partial derivative vectors. Okay, so that's where we're going to get all of this information, and I'm going to give you a couple examples on the next page. All right, example 9. Find the tangent plane to the surface with parametric equations given by x, y, and z at the point 1, 1, 3. Okay, so what we have, I'll just rewrite this, is the vector r of uv, which is made up of u squared, v squared, and u plus 2v. Really similar here to example 1, but we'll just do this using our new model with the vectors themselves. So we're going to find our partial derivative vectors. We have r of u, which is simply 2u, 0, and 1. And we have rv, which is 0, and 2v, and 2. Now we do have to do a little bit of work here because the point 1, 1, 3 is made up of x, y, and z. So what we need to do is figure out, Okay, what does that tell us about u and v? So remember, you can do this a couple different ways. You know that, for example, this gives us the information that x, which is equal to u squared, is now equal to 1. Well, that would mean that u is equal to positive or negative 1, for example. It can't be both values, so now you have to kind of dig into the next element. This would tell us that y, which is equal to v squared, is equal to 1. Okay, that ends up telling us that that v squared, v is equal to either plus or minus 1. Okay, so again, doesn't really help us a ton. We still have two options there. Now, if we look at z is equal to 3, which means that, if we had, for example, if u was 1 and v was 1, then everything is good. If they were negative, it would be bad, or if 1 was positive and 1 was negative, it would be bad. So in other words, what this tells us by induction here is that u is 1 as well as v. So you kind of have to work through the puzzle a little bit. Sometimes it's more obvious than others. You could probably do a lot of what I just walked you through just in your head and get to the answer. But anyway, that's the whole idea here, is that the point 113 is in Cartesian form. Okay, so let's take a look then at these vectors based on the information we have. So the vector r sub u, if we were to evaluate it at u equal to 1, would be simply just 2, 0, and 1. And then rv evaluated at v equal to 1 would be 0, 2, and 2. Okay, so those are our two tangent vectors in the direction of u and v. And now what we have to do is take the cross product of them in order to get our normal vector. So we're going to cross ru and rv, and I'm going to use the exact vectors because I don't need that to be in variable form. We left a lot of those in variable form in chapters 9 and 10 because we needed to. In this case, I'm going to use 2, 0, 1, 0, 2, 2. I'm not going to worry about the ones in blue in the variables because I don't need the variables in the end. Okay, so my cross product here will give me -2, -4, and 4. We could certainly scale this. I'm not going to bother right now. I'm just going to write down the answer. So we have a, which is -2, times x minus 1, minus 4, which is b, or -4 is b, I suppose, times y minus 1, and then 4 is c times z minus 3. So again, what I'm doing is I'm using the information that we have for the normal vector, which is in a, b, and c, and then I'm going to use the point, which is up here, and that point is going to be x sub 0, y sub 0, z sub 0. And so there you go. That's going to be your tangent plane. All right, let's do our last example. So suppose you need to know an equation for the tangent plane of the surface S at the point 2, 1, 3. You don't have an equation for S, but you know the curves r sub 1 and r sub 2 they both lie on S. So this kind of goes back to the visual on the previous page where you have curve 1 and curve 2. That's really what they're giving us. So they're not giving us the surface equation, they're giving us simply the curve equation, which is all that we need, because what we're going to figure out is the derivative or the tangent vector of each of these curves at the particular point. And we're going to use the cross product of them to calculate the normal vector of the tangent plane. So we're given enough information to handle the problem. Let's go ahead and take a look at the derivative of the first curve with respect to t. So we have 3, -2t, and -4 plus 2t. And then we have the derivative of the second one with respect to u. That's 2u and 6u squared and then 2. Okay, now what we're going to do is calculate, in this case, both of these tangent vectors. Now we're going to go with, again, we have the point 2, 1, 3. So we have to kind of dig through what is t and what is u. So for example, because both of these curves go through this point. So for example, the first curve, 2 plus 3t, must equal 2. And what that means is that t, let me write it this way, t must equal 0. Now, there's not a bunch of options here, so let's just make sure this works. So if we have 1 minus t squared, it must equal 1. Well, t has to be 0. We have 3 minus 4t plus t squared has to equal 3. Well, then if t is 0, it equals 3. So t is equal to 0. That's pretty obvious. Okay, let's tackle the next one. So the next one says that 1 plus u squared is equal to 2. So again, what I'm doing is I'm taking the first component and setting it equal to the first value I have in my point. And this gives us u equal to plus or minus 1. So not really good enough yet. Let's try the next one. 2u cubed minus 1 must equal 1. So I'm taking the second component and setting it equal to the second component of the point. Let's see, that's going to give me u cubed equal to 1. So we're going to get u equals positive 1 there. That's pretty definitive. So let's make sure that the third one works. So if I take 2 times 1 plus 1, I do get 3. So u must be 1. So we're going to take a look at our vectors now. R of, let's see, I'll write it up here. So we have this evaluated at t is 0. So my vector is 3, 0, and negative 4. And then I have u equal to 1, so I get 2, 6, and 2. And we're going to take the cross product of both of these vectors. And remember, I'm going to use the component or the numeric form. I'm not going to use the variable form. I don't need the variables after the cross product, so we might as well just make life a little easier and take the derivative, or excuse me, the cross product using our numeric values rather than variable values. Okay, so the cross product between these two. So I'm going to get 24 and see negative 14 and then 18. And then we can certainly scale that, but we might as well just finish the problem here. So we have 24 x minus 2 minus 14 times y minus 1 plus 18 times z minus 3 all equal to 0. And that will be your tangent plane. Okay, that does it for section 11.4. Thank you.